All right, so we had two videos that covered chapter 15, and chapter 15 was focused on the sun, but from the point of view of living on Earth and having that be in our sky and affecting us on a very real and very important basis. Chapter 16 also covers the sun, but it focuses on the sun as an example star, and kind of takes a step back from the fact that it's part of our solar system and focuses more on the kinds of observations that we can make about the sun that we can for other stars as well. A lot of the details that we saw in chapter 15 and a lot of the images that we saw in chapter 15 of the sun are pictures that we could not make for other stars because the sun is so close to us we can, and it's sort of its own special field to study solar physics compared to thinking about the sun as an example star in astronomy. Now, the very first section of the chapter 16.1, you can certainly read through the book, and it kind of describes the incorrect ideas that we had along the way to figure out how the sun works. The reason it's worth having one slide here is to make sure we understand that science is not about having the right idea all the time, very first thing, but about having a hypothesis and testing it against observations and throwing out that incorrect hypothesis if it's wrong. That's still good science. So the very first idea that people had for how the sun was powered, and when we talk about how it's powered, it's like how is it able to make light and heat and all of this energy, because you can't create energy out of nothing. So the first idea was that comets or meteorites or asteroids were falling into the sun. This general idea is kind of like a coal furnace. You have to throw in physical material to be burned up, and that was the original idea because it was something that people were aware of on Earth as a fuel source, and it's pretty hard to think about why that would make sense with our 21st century thinking, but without better understanding of the underlying physics, it made enough sense at the time. It is, however, very easy to disprove. You can figure out how much mass you would have to be throwing at the sun every single year, basically how much coal you're shoveling into the furnace, and that amount of added mass would change the force of gravity in a measurable way from one year to the next and from one decade to the next. So because we weren't seeing any kind of change in the force of gravity, we could easily disprove that hypothesis, and we had to throw out that idea. The next big idea that caught on for a while is called gravitational contraction. This makes more sense because it was what was powering the sun before the sun turned on, and we'll talk about what that means in a little bit. And it is currently happening with Jupiter. The planet Jupiter actually emits more energy in infrared and radio waves than it receives from the sun. So Jupiter is sending off more energy than it receives, and the reason for that is because it is contracting down. Gravity's kind of pulling it into a slightly tighter ball from one year to the next, and that is taking gravitational potential energy and basically converting it into heat and light. So gravitational contraction exists. It is a process that powers things. Stars, before they become stars, are called protostars. And gravitational contraction is taking a bigger ball of plasma and bringing it down into the eventual stable size, releasing energy and light during that process. But if we went through the calculations, which even when this was an idea, was physics that people were aware of, it would mean that the sun was only 100 million years old, which seems nice and long enough if you don't have any sense of how old the solar system is. But once we had radioactive dating measurements that show that the solar system is 4.5 billion years old, then we knew that gravitational contraction couldn't work. The sun would have collapsed itself down in that period of time if that's how it was powering itself. So again, we have the hypothesis proven false. We have to throw it out. In both of those examples, though, what we notice is that we had to explain a source of energy that could be turned into heat and light. The rest of this video is going to be on section 16.2 because this section is really important for laying the groundwork for how the sun is powered, and then we'll finish up chapter 16 in a different video. So in those two ideas from section 16.1, in both cases we had to have an energy source that we were converting, because one of the four quantities in physics that always has to be conserved is energy. The others are linear momentum, which in collisions is how we can figure out how fast stuff is going to move after it hits something. Angular momentum, which has a lot to do with orbits and how orbits work and how they're able to change. And electric charge, which is going to come up in a couple of slides, but not in a way that we have to worry about. Mostly this list is just for those who are curious. There's only so many things in physics that have this really fundamental property that they can't be created out of nothing or destroyed completely. Now, one of the most important things to keep in mind, though, when we're talking about the conservation of energy, is that mass is also a way to store energy. Albert Einstein's probably one of the most famous and well-recognized scientists of our sort of modern understanding. And even if we don't quite know all of his accomplishments, the one equation that is probably most well associated with him, even if we don't know what it means, is E equals mc squared. Somebody writes that down and you think Albert Einstein, genius, whatever. But the point is that equation is very straightforward. We actually already know what c is. It's from chapter 5, the speed of light. It's that same value c. And all this equation is telling us is that energy and mass are kind of interchangeable or equivalent. And we use that c squared term to be able to tell us how much energy could be turned into mass and vice versa, because they aren't just a one-for-one correlation. So mass is not conserved in its own sense, because if you burn firewood in a fire, you have less mass of ashes than you did with wood at the start, but that's because you turned some of that mass into energy to heat your house. The other thing that we need to remember from chapter 5, and we can either use this as our brief reminder or go back to those videos even, is the atom has a particular structure. It's got an internal nucleus and electrons that orbit around that nucleus, or at least exist around that nucleus in the electron cloud. And as a reminder, those fundamental pieces that we introduced in chapter 5 were protons, which have a positive charge and quite a bit of mass, neutrons, which have no charge and have about the same amount of mass as a proton, and electrons, which have very little mass compared to protons or neutrons, and they have a negative charge. Okay, so we talked about all of those, and that is perfectly fine. But that's not the only fundamental particles that exist. It's just the only ones that show up in an atom on a regular basis. Every particle has an antiparticle. So if you've ever heard the term antimatter in science fiction, it's not just science fiction, it is a real thing. Antimatter is real. We just don't have it floating around anywhere, because anytime that you have a particle and its antiparticle that find each other, they'll annihilate each other. They'll both disappear and become energy. Because again, energy can't be created or destroyed, but you can turn that matter into pure energy. And that's what happens if we have matter find its antimatter pair. The only one that we're going to introduce here is for the electron. The anti-electron is called a positron. And we'll see in a couple of slides why we wanted to all of a sudden introduce it here, because we need it. And then additionally, for our list of things that might show up as we talk about how the sun powers itself, in the 1930s, when scientists were going through a whole bunch of research of basically smashing atoms together and seeing what happens, in certain nuclear reactions, it seemed like all of a sudden we had broken physics. The amount of mass going into the reaction didn't match the amount of mass and energy coming out. So we were struck with a situation where we either have to throw out that physical understanding of energy conservation and decide that hypothesis is proven false, or we have to figure out what we're missing from our experiments. So to explain this, Wolfgang Pauli basically invented a massless particle, and he called it the neutrino. So a photon is a light particle. We've talked about photons in chapter 5. Photons have no mass, and so they can move at the speed of light. But photons we can very easily observe, so we knew that what we were missing wasn't a photon. Instead, we had to come up with a different particle that seemed like it could move at the speed of light and wouldn't actually interact with anything, which means it would be undiscoverable. So it wasn't that Pauli found these neutrinos. He basically invented the idea of neutrinos in the 1930s. I'm going to sort of give us a spoiler alert. We have since discovered a process to measure neutrinos and detect them, and we'll talk about that at the very end of this video. But the neutrino is something that is, as we now know it, not actually perfectly without mass. It is much, much less mass than an electron, but it doesn't move at exactly the speed of light. It is not perfectly massless like a photon. This table is from the textbook. You can always go back and find it. And we don't need to memorize any of this information. But what we do want to point out is the neutrino is not perfectly massless, and we know that it can't be above a certain mass, which is already almost 10,000 times less mass than an electron. But we don't have a perfectly defined mass for it the way that we do for these other fundamental particles, because it is hard to detect, and we'll talk about that later. The other thing to note is that protons positive charge, neutrons no charge, electrons negative charge, and then neutrino, tiny neutral one, also has no charge. Okay, so we've laid the groundwork for what it is that we might see in the reactions that we're going to introduce. The other incredibly important thing for us to understand is the difference between fusion and fission. This is very important. Now, fusion is when we take two smaller particles and we bring it together to make one bigger particle. So at the end, we have a slightly larger nucleus. This is what stars are going to be using to power themselves. And it's also what the hydrogen bomb or the H-bomb used for a short amount of energy generation. Fission is when we split larger things, a larger single thing, into smaller pieces so that we end up with multiple pieces at the end. This is what we use on Earth in nuclear reactors. We take uranium and we split it apart and we get energy out of that process. And it's also what the atomic bomb or the A-bomb used for, again, short-term amounts of very large energy generation. So we want to make sure that we have those separate in our notes and separate in our minds. Fusion is taking multiple tiny things and making a bigger thing. Fission is taking one big thing and making multiple smaller things. This picture here is going to show up when we need it in like chapter 23, 24. But I want to introduce it briefly right now. When we go from the left to the right on the chart, we're going to bigger mass numbers, which means we're going through fusion. When we go from right to left on the chart, we're going from bigger mass numbers to smaller mass numbers, and that means we're going through fission. We can go in either direction as far as we want to, but if we're trying to get energy out of the process, if we're trying to produce energy, we have to go down this curve. We have to go from higher to lower on the way that this curve is shown. Now, if we look, hydrogen is way up top, and so going from hydrogen to something bigger is going to give us a lot of energy. And uranium on the far right of our image, that's what we break apart to get energy, and that's going down the curve too. And if we look, iron is indicated right at the bottom of that curve. That is going to be something that is very important to our discussion of how high mass stars die. The fact that something had to be at the bottom of the curve and it happens to be iron. That fact that iron happens to be, through chemistry, the most tightly bound nucleus is why iron is more abundant than a lot of other things. It's the reason that we have iron in our blood, is because stars will make iron but won't go past that. But that's sort of foreshadowing for a later chapter. For now, our big goal was to make sure we understood the difference between fusion and fission. Okay, now the big reason that we can't use nuclear fusion here on Earth, because it would be a lot more effective, we're going further down the curve, and it wouldn't produce radioactive byproducts, which is a problem for our nuclear reactors, one that we deal with fairly well, but is still something we have to deal with. The reason that we can't use nuclear fusion is because it requires incredibly high temperatures and densities. We can actually, in the 21st century, we can do nuclear fusion in very, very small volumes in a controlled lab environment for very short periods of time. But in order to set up the plasma to be at the right temperature and density, we had to put a lot of energy into setting it up, which means it's not actually an effective process yet for us to use for energy generation. In the core of the sun, the temperature is well above the minimum needed to turn hydrogen into something bigger. And so we're going to see what that process looks like. This process is called the proton-proton chain. We need to have that term in our minds. We do not need to memorize the internal steps. I am going to show them to us so that we can see what it is that's being made, because a lot of the byproducts of this proton-proton chain are what we care about, because it's all the heat and light. So we're going to go through. There's 3 steps to the proton-proton chain. The first step is that 2 hydrogen nuclei, which are basically just a single proton, they hit each other and they fuse together. If we take 2 protons, then what we think should happen is that they should just stick together and we have something that is now 2 protons. That actually turns out to be not chemically stable, and so one of those 2 protons decays down into a neutron, and because all of a sudden we have less positive charge than we did before, we make a positron. Now remember, that word positron we actually introduced already in this video. A positron is an anti-electron. It has the same mass as an electron but the opposite charge. And if we count up how much energy went in and came out, we actually need a neutrino there also to balance the energy for energy conservation. Again, we don't need to memorize what goes in and what comes out of each of these internal steps, but we're trying to describe why neutrinos and positrons are coming out of this when it seems kind of like magic. The second step that happens is one of those deuterium atoms, the proton plus neutron that got made in step 1, finds another proton to smash into. And then those 3 things just all kind of stick together to make a helium-3 nucleus. It's an isotope of helium. We learned that word isotope back in chapter 5, just version of. And for energy conservation, a high-energy gamma-ray photon carries away the extra energy that didn't go into that process. Again, because we're going down that curve, we're releasing energy, and that's one of the ways that we do so. And then step 3 is 2 of those helium-3 isotopes that we made find each other, they smash together, and we get one slightly bigger thing, but some of the protons come back off again, and which means they get to try again and start the process all over again. Now, this whole slide here, on the right side of the slide, the image is showing us the step-by-step process that's happening. We do not need to memorize that step-by-step process. What we do need in our notes and in our brains is that the proton-proton chain takes 4 hydrogen nuclei and creates 1 helium nucleus. So hydrogen is being fused into helium. And then extra energy is coming off of that in order to have energy conservation. The energy gain comes from Einstein's idea of E equals mc squared. We look at how much mass 4 protons have compared to how much mass a helium-4 nucleus has. And there's less mass at the end, which means that got turned into energy. In order to resist its own gravity, the sun actually has to convert 4 million tons of hydrogen into helium every single second in order to basically push back against gravity. Now, the other things that we found as we went through the proton-proton chain, and again, the reason I showed us the internal steps is so that we could see why we're making gamma rays, positrons, and neutrinos. We don't need to get into the complex chemistry, and we don't need to memorize the internal order, but it's worth making sure we know where those byproducts went. Gamma rays are light photons. They'll immediately get absorbed and re-emitted by atoms, and we'll see what that absorption and re-emission process happens. Every time they get absorbed and re-emitted, they tend to go down in energy because they're kind of being re-emitted in steps. So although the sun is producing all gamma rays, they don't end up being all gamma rays by the time they get out to the photosphere. Positrons, when we introduced that term, we said they were anti-electrons. As soon as they find a free random electron flying around, they'll both annihilate, they'll make new gamma rays, and then we talked about what happens to gamma rays. They kind of get absorbed and re-emitted in steps. And the neutrinos, they're just going to escape the sun. We're going to come back to them in the very last portion of this particular chapter. It's going to be a separate video when we talk about section 16.4. So I'm going to leave this video here because we've covered enough for one sitting. You're certainly welcome to jump into the next video right away, but the key thing is that the proton-proton chain is the term that we want to have in our minds for what powers the sun. It is a fusion process, and it turns hydrogen into helium. All right, I'll see you in the next video.